I don't know how we got off. You guys were pretty good at that. You got me off on that tangent and pretty. Yeah. Yeah. Okay, so I want to do something. We're gonna do something kind of fun here, though. I want you to. We're gonna use physics to solve a practical problem that you might find yourself in today. Okay, so what are we gonna? We're moving into the next chapter, and what this chapter is about. Let me just give you a little bit of an overview. Why don't you put all your phones and that stuff away? Now we're getting into official things here. We're going to start talking about motion and dynamics, forces in more than one dimension. Everything that we've done has essentially been in one dimension. Even when it looked like it was going to be in two dimensions, it really wasn't. It was one dimension. Right? We had, if we were pushing a box along a surface, and this is the most complicated situation we probably looked at, was frictional situation, where if we're pushing the box, that's our pushing force. There's our frictional force that's resisting us. The weight pushed down and the normal force pushed up. That's pretty convenient. All those forces occurred either horizontally or vertically, right? Okay, which made us able to deal with this essentially one dimension at a time, right? We could look at the normal force and the weight vertically, and we could look at the friction and the pushing force horizontally. Things get a little more complicated, though, when you're not limited to just one dimension, right? Like, what if, for example, we want to study the motion of a box on an inclined plane, on a ramp or something, right? Now you got, things are complicated a little bit. If we thought about all the forces, and we'll look at this, probably not today, but within a few days, we'll be, or maybe right after the next semester, we'll start to look at this in more detail. But even now, name the forces that are acting and the directions that they're acting. I bet you can on that box. Okay, so gravity acts in what direction? Down. Good. So gravity acts like this, doesn't it? Okay. What else? Okay. How about normal force? In what direction is normal force going to act? Now, those of you in calculus, think what normal means. Off to the
maybe perpendicular to that.
Yeah, like that. Normal means perpendicular. Normal force always acts perpendicular to the surface, right? Because what is the normal force? The normal force is the strength of interaction between the two surfaces, and that's why friction depends on it, right? I don't necessarily have the right lengths, but we're just looking at directions for now. What else? Okay, let's say it's sliding. Okay, if it's sliding, we got some friction acting. In what direction is the friction acting?
Down.
Okay, so if it's sliding down the ramp, then the friction would be acting in that direction, right? Okay, and maybe, let's say maybe I'm pulling on this thing with a line. So maybe I've got a tension force there too, right? And so I could, if I want to make it simple, maybe I've got the tension force acting in that direction. But maybe I'm going to make it harder and I've got the tension acting at a different angle. Say I want to make it a little tougher. What if we've got the tension acting like in that direction? Okay, do you see a problem there? Well, that's a mess, isn't it? Those forces are all acting in all kinds of different directions. What do you suppose I'm going to want to do with this to be able to handle all those vectors acting in so many weird directions? What do you think? Okay, yeah, I'm going to want to, in order for me to be able to deal with this, I'm going to need to take all those forces and I'm going to need to break them up into components. And you might remember we spent quite a bit of time breaking vectors up into components. Now, what do you think would be probably the most convenient coordinates for me to use here? X and Y is a pretty good bet, isn't it? But in this case, I'd say no. X and Y would mean horizontal and vertical. And if you look at the motion of this crate, well, not really even north and south. What I'm saying is a lot of times when you want to look at how you're going to break down the forces acting on an object, a good bet would be to say, in what direction is that object going to move? And that's probably one of the directions that we'd like to choose. If this thing is, where's it probably going to move here? It's going to slide down the ramp, isn't it?
Yeah.
Right? So if we wanted to identify a coordinate system that's going to match this picture, this is a pretty good coordinate system. We're going to have this direction be one of our directions. Now we might call that the parallel direction. So a lot of times what I'll do is I'll break this up into, like if we're going to talk about, let's say for example, the gravitational force, mg. We could call that the parallel component because it's parallel to the surface. And if that's the parallel component, whenever we talk about coordinate systems like x, y, z, what's always true of the other coordinates? They're perpendicular, right? So if this is one of our directions, then this has to be the other. So we'd have components like the parallel component of weight and the perpendicular component of weight, right?
So where's the
Right?
Say it again.
Wouldn't that just be Fn?
Well, I mean, maybe it's related to that, but not necessarily.
But like Fn is well that the sliding down is parallel to the ramp, right?
Yeah,
And then Fn is perpendicular to the ramp. So
you're right. Okay, but you're onto something, but what about the tension here? See, the tension is not acting parallel, so it's gonna have components of both too.
Yeah, but I was meaning like the normal force is gonna be
The normal force already is completely perpendicular, and the friction is already completely parallel. But the other two forces would have to be broken into components. That's just a vision of kind of where we're going with this. We're not gonna do that today necessarily, right? But I just want to show you that that's how we're gonna deal with this. Is we're going to, just like we did with the friction examples from chapter 6. Remember, we always took these friction examples and said, okay, we could break this up into equations of motion, right? We could say that the net force in the y direction, right, vertically, was equal to the positive vertical force was the normal force, and mg points down, which is the negative vertical direction, so we would subtract mg, and that equals ma, the vertical component of acceleration, which is what? Is this, when we were dealing with friction with an object sliding horizontally along the ground, was there any vertical acceleration? No, it was 0, right? So this was just equal to 0, and so that told us that normal force equaled mg, right? That was one equation of motion. And what we mean by it, we didn't make such a big deal about it then because things always worked out nicely. But the equations of motion are just, once we know what the two right angle, the technical word is orthogonal, the two orthogonal coordinate directions are, we're just going to break the forces down into the forces along one of those directions, which was vertical for us before, and the net force in the perpendicular or horizontal direction. What was it here? We had, horizontally, we had the pushing force, right, minus the frictional force, equaled m times the acceleration in the horizontal direction. Maybe we did have acceleration in the horizontal direction. In some cases we did, right? So that was the other equation of motion, okay? Friction ended up being kind of related to the other equation of motion by the fact that friction equals mu times normal force, right? So this was important to us, and it played a role in how we were able to maybe solve for acceleration down here. But really, we just had these two equations of motion, right? We're going to do the same thing in the future, in this chapter, only now we're going to have to, when we break down, for example, let's say we want to find the net force in the parallel direction. Okay, let's define, and we need to define what are the positive directions for our coordinates too, because we can do that. It's just arbitrary that we say up is positive and down is negative. But we could have easily, we could say down is positive, as long as we're consistent, and everything will still work. For this one, we'd probably say down the ramp is positive, maybe. Okay, I mean, it's up to you, but usually we do. And normal, pointing away from the ramp, normal would be positive. Totally up to you though. I mean, you can change that. But if we did that, the parallel component of normal force would be what? Well, what could we do? Like with this mg, I mean not normal force, but the net force, sorry. This mg, we could really break that down, couldn't we? We could trade that for components, just like we did before, right?
Yeah.
We could kind of get rid of, whoops. We could get rid of this downward weight vector and trade it for a perpendicular component and a parallel component, right?
Yes.
We would call this one mg parallel maybe, and this one mg perpendicular.
Wait, when did you get the video here?
No.
He has it written down right, he just wrote, he said.
Oh, did I say them backwards?
Yeah, he said-
Oh, okay, whoops.
You have it written
mg parallel and mg perpendicular.
Wait, I thought we were gonna get back then.
Oh, we're doing the net force. Okay, we're just doing the net force. I meant to say net force. Sorry. So the net force, the parallel component of the net force would then have, if we're saying this is the positive direction, mg parallel, whatever that is, it's just going to involve maybe some sines and cosines, right? But we'll get there later. That's going to be a positive contributor, isn't it? Right? What about the tension force? Okay, we could trade the tension force for components also, right? We could trade the tension force for a parallel component and a perpendicular component, right? In this case, the parallel component would be positive, right? Are there any vectors that are pointing in the negative parallel direction? Friction does, right? So minus frictional force equals m times the parallel component of the acceleration. There's one equation of motion. And we'll go back later and we'll say, okay, well, what is that component? It's going to be mg sine theta or mg cosine theta every time. And we'll just look at it and we'll have to kind of draw a picture and maybe see, right? But we'll get there later. What about the vertical equation of motion? Now we've got the perpendicular component of the net force. What are the perpendicular players in this game? Well, we said positive is up, so are there any positive ones?
Normal force.
Normal force. So we get normal force. Any other positive ones?
Tension.
Tension, right? The perpendicular component of tension. So we get plus T perpendicular, and then any negative ones?
Mg weight, nuclear.
Yeah, minus mg perpendicular. And what would that be equal to?
Would that be MA perpendicular?
Okay, it's going to be the mass times the perpendicular component of acceleration.
Oh, so gravity.
But in what direction is the crate actually moving?
Yeah.
It's moving parallel only, right? It's not moving perpendicular at all, right?
No.
This thing, if we look at the box, it's just going to slide down in the parallel direction. It's not going to accelerate off the ramp spontaneously, nor is it going to accelerate into the ramp, right?
It's true, so.
Couldn't it when if you like pulled that thing on?
Well, if I pulled it hard enough, but let's say we're not going to pull it that hard, let's say, okay?
Should we be thinking?
No, you don't have
Be
to.
zero.
You don't have to. So this would be zero, wouldn't it? And those are our equations of motion, right? And so then, from those equations of motion, either we have enough information to answer the question we want to answer, or we don't, right? But I'll make it so we do. Okay?
Okay.
You kind of get the idea?
Yeah.
So it's not that scary, right? It's the same stuff we were doing before, only difference being that we're just gonna have to pick, instead of just using X and Y, we're gonna have to, based on the problem, we're gonna have to pick what are our directions gonna be and then break all the vectors up into components. Yes?
Couldn't you do this problem also just like physics wise? Couldn't you just take out the tension and make it mg? Because like the box would slide down as long as it had enough.
You're right,
weight.
okay, but the tension's maybe gonna further accelerate.
Okay, yeah, but you wouldn't need it for it to do the equation, right?
Well, I mean, to do,
As long as the box was accelerating.
okay, but if the tension, if you really were pulling on the box, then you'd have to take that into account.
Yeah.
And if you're pulling on the box, just to kind of, if I'm pulling on the box at that angle, if I'm pulling on the box horizontally, look what it's doing. It's kind of doing two things. it's contributing, the tension is contributing a parallel component of force that's going to increase the acceleration, right? And it's contributing a vertical component that's actually going to probably decrease the normal force, isn't it? Right? Because these things, see what I'm saying? Because these things have to add to zero. And so if they have to add to zero, the weight is just based on the mass of the object, right?
Right.
So these two things have to add together to offset the perpendicular component of weight. And if the tension is bigger, that means the normal force would be smaller. What's that going to do to the friction? Decrease it, yeah. Right? So, but the equations take all that into account. That's the great thing about physics. I mean, it's all right there. The whole story is told in those equations, yeah.
So is that how you get like a time when you pull something off the slope is when like tension is higher than friction? Or the-
Yeah, that's why, well, okay, that's why if you were gonna pull, like, if you were trying to pull something across the ground, there would be a point where it would be, and we can, in calculus, we could actually figure this out later in the year. You could figure out what's the optimum angle, right? Because there's gonna be a certain angle where you're gonna still get quite a bit of force horizontally, but you get enough force vertically that reduces friction a little bit. See what I'm saying? And so there's gonna be some angle where it's gonna be the best angle.
Is that like when, like kind of lifts off?
Well, it probably wouldn't even lift off the ground, it maybe just reduces the friction enough that it slides more easily. Okay?
So you
That's
wouldn't
like when
wanna
you lift
pull
the
it, but then like.
Yeah, so you're lifting, and it's why, like in football, a blocker, the best blocking technique would be to get low to the ground and kind of push up and into the defender. How come?
Because they're having less traction.
Yeah, because his weight increases your friction, right? And you're pushing him off the ground, so it decreases his friction, and so you can slide him backwards, like if you're on the offensive line, right? That's how they would do it. Or defensive line, yeah, exactly, yeah. Okay,
4 minutes.
so, okay, here's the puzzler. Here's the puzzler I want you to see if you can, and don't cheat, don't look, I mean, I don't know if this will be on Google or not, but don't Google it. See if you can come up with a solution to this, and this is what we'll talk about next time we talk about new stuff. Here's the situation you're in. Let's say that you're out in a remote part of the wilderness, and you get your car stuck in the mud, and your cell phone is busted, you don't have any cell service, and you're kind of, the weather's threatening, here's what you have available to you. You can't get the car out because the wheel is spinning. You don't have a jack, you don't have anything like that, but what you do have is, let's say that you have a tow rope in your car. You have a tow rope, okay, and you're around, let's say that it's a pretty long tow rope, and you are 100 feet away from a big, strong tree, okay? Is there a way that you could, and there's 2 people, you and your buddy, let's say, is there a way that you could maybe move your car a little bit, just enough so that it gets out of the rut and you get traction? That's all you gotta do, okay? But your car's heavy. Right?
With the rope.
Why would the tow rope?
So now in your car,
You could use it as like a pulley, the tree as a pulley. You
okay,
could also use the tree and take a branch from the tree and tie it to your tire, and that works too.
okay, but the thing is, your car's in there so far that you just can't get anything under the tire to give you any additional traction. So you've tried
You
that.
said they were spinning though, so you
So here's your car from above. There's your car. There's the big rut that your wheels are in. Here's the trunk of the tree seen from above, and you have a place to tie the tow rope. I want to know, how could you get the car, and you could do this, seriously. This is something that a person could do. I'm not just, I've actually done something like this before, I promise you.
So like you would tie the rope to like the under the hood, or not like under the hood, but like under the
axle.
Yeah, like under the.
So you have a place, let's say you have a tow hook on your car even.
And then like you tie it higher up on the tree.
Well, where you tie it, you just think about this a little bit. It'll all make sense when we go through it next time, but there is a really good strategy that would potentially get you unstuck here. And it wouldn't take any kind of superhuman strength to do it.
I think I'm just gonna find it.
No.
Just saying, it's over with the tire, and a really nice word.
I'll tell you something else. It has nothing to do with lifting the car.
Why would you deploy the word?
There's your challenge.